Hello everyone, in this video we are going to derive the shape functions of a beam element. Now why do you want to derive the shape functions of a beam element? Well, you have to derive the shape functions of a beam element, only then you can derive the stiffness matrix. So deriving the shape functions, they are the prerequisite to derive the stiffness matrix. And you have to find the stiffness matrix so that you can solve the global finite element equation K matrix into U matrix is equal to F matrix. To find the values of displacements, and once you know the values of displacements, you can find the strains. And once you know the values of the strains, you can find the values of the stresses. And once you know the values of the stresses, you can take some very smart engineering decision. Okay, just imagine that we have got a very complicated beam like the one that you see here. Now in this beam, the first part is made out of steel, the second part is made out of concrete, the third part, the moment of inertia changes then. The cross-sectional area changes, so you can see clearly the moment of inertia changes, and also the left-hand side of the beam is fixed, the right-hand side there is a roller support. And if you want to solve this problem by the conventional strength of materials method, it becomes very difficult for you to solve the problem. So what you do, you solve it by finite element method. In finite element method, the first step is discretization. You divide the given structure into known geometric elements. So for the sake of doing the mathematics in a very easy way, what I have done here is I have divided the structure into 4 elements. In actual practice, the software can even divide the structure into thousands or even millions of elements. Now I have pulled out one element, that is element number 2, that is made out of concrete, and I assume that it is homogeneous. Throughout element number 2, the moment of inertia is going to be the same, the material is going to be the same. So material property and geometric property and the loading conditions should not change throughout the element. All right. Now the first step to derive the shape functions is to assume a trial solution. So this is the trial solution that we are going to assume. It is a0 plus a1x plus a2x square plus a3x cube. Now why do I assume the trial solution? Understand, first dv by dx, dv by dx is actually slope, theta. And what is EI into d square v over dx square? Well, that stands for the bending moment. That is the expression for bending moment. If you have difficulty in understanding how that can be the expression for bending moment, I highly recommend that you watch the video on the derivation of the governing differential equation of your beam. There I have given the proof that EI into d square v over dx square is actually bending moment. And also EI d cube v by dx cube is shear force. So clearly, if you want to find the bending stress, you have to use the 100-year-old bending equation, which is m by I is equal to sigma by y is equal to E over R. You can find the expression for bending stress if you know the expression for bending moment. So clearly, to find the bending stress, you should assume a trial solution that is differentiable 2 times. And if you want to find the shear force, which is given by this expression, shear force, I'm sorry about the terrible handwriting. If you want to find the shear force, you have to find EI d cube v over dx cube, which means you have to assume a trial solution that is differentiable 3 times. All right, this is the first step, that is assuming a trial solution, and that is over. The second step is to apply the boundary conditions. We have 4 boundary conditions. The first boundary condition, at x is equal to 0, at the left extreme end of the beam element, the value of deflection is v1, right? The value of deflection of the beam, here we go. This point, right, for element number 2 is getting deflected along the vertically downward direction by an amount v1. And this point is getting deflected along the vertically downward direction by an amount v2. So they are boundary conditions. one set of boundary conditions. I'm sorry. What about the next boundary condition? At x is equal to 0, the value of the slope, which is given by the expression dv over dx. At x is equal to 0, that is theta 1. At x is equal to L, that is theta 2. That is given here. So these are the boundary conditions. v1, v2, theta 1, theta 2. These are the sets of boundary conditions. Now all I'm going to do is I'm going to apply these boundary conditions in the trial solution. So here is the trial solution that you see on the right hand side. And what I'm going to do is I'm going to put x is equal to 0. The value of v becomes v1. At x is equal to 0, this term disappears, and this term disappears, and also this term disappears when you put x is equal to 0, and also the value of v becomes v1. When you put v is equal to v1, then a0 becomes v1, so you get this expression. At x is equal to 0 also, the value of theta becomes theta 1. So theta is dv over dx. If you differentiate the trial solution, you get this expression. At x is equal to 0, the value of dv over dx becomes theta 1. The other terms in dv by dx where you have x, they disappears. So the value of a1 is theta 1. So you get this expression. The third boundary condition at x is equal to L. The value of v is v2. So you put at x is equal to L in the trial solution. V becomes v2. And already the value of a0 is v1, so it's v1, and already the value of a1 is theta 1. So you substitute those values, you get this expression, and you rearrange this equation, and you get an equation in terms of a2 and a3, assuming that that is going to be our star equation number 1. You see, that is our star equation number 1, and you see in star equation number 1 you have two unknowns, a2 and a3. And you know where the story is heading. If you have two unknowns, you can come up with two equations to solve the two unknowns. So finally applying the last boundary condition at x is equal to L, the value of theta is theta 2. You get this expression. You apply this boundary condition on this equation right here. The value of theta becomes theta 2. You know the value of a1 and a2, plug that here, rearrange this equation to get star equation number 2. Okay, now I'm going to solve the two star equations. So what I do, I want to cancel the a2 term. So in order to cancel the a2 term, I'm going to hit the first star equation by number 2. So if I hit the first star equation by number 2, this is what I'll be getting. First star equation, multiply that by number 2, I get this expression. Then I'm going to hit the second star equation. This time I'm going to hit the second star equation by L. And if I hit the second star equation by L, all I end up getting is this equation. So this is star equation number 2, and I'm hitting that with L. Now I subtract the two equations to get the value of a3. So I got the value of a3 in exactly the same manner. I can cancel the a2 terms to get the, cancel the a3 terms in order to get the value of a2. So that's what I have done here. In order to do that, what I do, I hit the first star equation by the number 3. So if I hit the first star equation by number 3, I get this expression, and I have to hit the second star equation by the number, let me check. So the second star equation, what is that you are hitting that with? Well, the second star equation, you have to hit it with L. So if I hit the second star equation by L, I get this expression. I solve the two equations to get the values of a2, to get the value of a2. So this is the value of a2. Now I have the values of a0, a1, a2, and a3. All I do is I take those values and plug it back in the trial solution. If I put them back in the trial solution, the value of a0, a1, a2, and a3, I get this expression. Then finally, rearranging them, that is, all I do is I pull the coefficients of v1, the coefficient of v1 here, just for one example, it's 1, and the coefficient of v1 here, it's minus 3 by L square into x square, and the coefficient of v1 here, it's 2 by L cube into x cube, right? So that's all the coefficients of v1 multiplied by v1. And similarly, all the coefficients of θ1 multiplied by θ1, all the coefficients of v2 multiplied by v2, all the coefficients of θ2 multiplied by θ2. So this is of the form n1 v1 plus n2 θ1 plus n3 v2 plus n4 θ2. So v of x, the deflection is of this form. So this is the expression, these are the shape functions for a beam element. Now, as I told you, the shape functions are prerequisites to derive the stiffness matrix. We will do that in the next video. We will have the weak form expression for a beam element, and we will derive the stiffness matrix of a beam element. Thank you all for your patience. Thank you so much.